Hello again. I'm back and it's April Fool's Day for this video, so I thought I'd wear my rainbow squid hat and still got the rose-colored glasses on. So we're on page 6 of your notes for those of you who are able to print, and we're doing formal charges. And in case you don't have your Fool's hat on or your formal attire, you can pause me and go get dressed up for formal charges. All right, so formal charges, they help us to see if we draw a picture, if it's reasonable. So the example I have is OCN, and making sure those of you watching the video can see that. Oh, beautiful. So there's a couple different ways. There's actually 9 different ways we could potentially draw this. There's only one way that is going to be correct. So we're going to do all of them with, we'll do 4 different ways. How's that? We can do oxygen, nitrogen, carbon in the middle. Of course, because carbon loves to be in the middle. It's the least electronegative if you've done your practice with Lewis structures. All right, forgot to count electrons. So oxygen, 6 valence electrons, carbon has 4, nitrogen has 5. So 6 plus 4 plus 5, oh, and we have a negative charge, so we're going to add 1 more. So it's 16 valence electrons for all the ways that we draw this. All right, we would give the octet to the outside. And we've run out of electrons. This is where we make multiple bonds. And this is 3 of the possibilities. So keeping carbon in the middle each time for our first 3 possibilities, there we're going to need to share more electrons 2 more times. So typically you want to do a double and a double. That's like, we'd like everything to be symmetrical, equaled out. But it turns out, if you've been watching this, and remember the original, my intro video on electronegativity, oxygen's really greedy and it doesn't want to share. And so it's going to make nitrogen do the triple bond, share, 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 and oxygen keeps as many of its own. Or maybe we could go the other way. Oxygen has to share, 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 and nitrogen keeps a lot of its own. Now, without formal charges, you can all tell me which one is the best, just based on good reasoning skills. But formal charges is a mathematical way. So if I was going to pick the best one, I would pick the middle one. So pretend like it's a test question. And I would say, why? Why did you pick this middle one? So I can call on, we have the cow has to hold up our polar bear because this chalkboard doesn't have enough ledge. So Mama Polar Bear says the middle one, because oxygen's so greedy, it doesn't want to share unless it has to. And if we had a molecule like CO2 where the oxygens were on each side, of course you would get double bonds on both sides because one of the oxygens isn't going to take more than the other. But formal charges is a mathematical way to do this. And I'm sure you can Google or look in the book that I posted for you, and they'll give you a slightly different definition, but you get the same answer doing it my shortcut way, which is you take the group number for the element minus the lines plus the dots. So rather than counting electrons, we're going to count lines and dots. So if we look at carbon, in every case, carbon is group number 4. So we put it as 4, and then we subtract the lines. There's no dots in any of my carbons. So we'd have 4 minus 4. So every time, carbon is going to be a 0. All right, for nitrogen, nitrogen is group 5. And so nitrogen, on this one, has 4 dots and 2 lines. So we'd have 5 minus 6. So it gets to be a negative 1. On this one, it would be 5 minus 5. So 2 dots, 3 lines. So we get a 0. Ooh, that one's looking good. And then on this one, we would have nitrogen, I'll write it underneath, 5 minus 6 dots in 1 line. So 5 minus 7 is negative 2. And right, already you can say negative 2. That seems like a large number. All right, let's do the oxygens. Oxygen is in group 6A. So again, we're using the A group numbers, the old numbering way. So 6 minus 4 dots and 2 lines, 6 minus 6, and we get a 0. On this one, we'd have 6 minus 7, so 6 dots in 1 line, so 6 minus 7, we get a negative 1 for the oxygen. And then on this one, we would have 6 minus 5, which is a plus 1. Now, formal charges, advantage is that it's a mathematical way of saying which one is most reasonable. So the last one is not, because the formal charges are the largest. So this gets a big frowny face. But why did I pick the middle one over the top way that I drew it? They both have 0, 0 and a negative 1, and it has to do where the negative 1 is. If you have a negative charge, a negative formal charge, you would want it on the more electronegative. So the middle one wins as the best picture because the negative is on the more electronegative atom. So on a midterm, when I ask that question or on your worksheet, you don't just say because the negative's on the oxygen, you would get most credit. You would say it's on the oxygen because the oxygen's the greediest or the most electronegative. Something to remember that your teacher has already admitted, she forgets often, that we weren't supposed to show brackets around each of these with a negative charge on the outside. In all honesty, I'm not a big stickler about that because, as you've noticed, I'm extremely human and humbled by this video making fun. And so our middle picture wins, gets the gold star or the white star, and the more electronegative. The sum of your formal charges must be equal to the charge of the compound. And so if you had a neutral compound, and we'll do one of these practice on the last page, the practice page, but that's the idea of formal charges. It allows you to mathematically prove why that would be the best choice. Now, I said I would do one more. I'd do a fourth one. I said there were 9 possibilities, and the other possibilities would be if you don't put the carbon in the middle, which makes no sense at all. Let's put the oxygen in the middle, and we can double bond to nitrogen and double bond to the carbon. You could double bond to each one. You could triple, single, single, triple. You could put the nitrogen in the middle. So there's 3 ways with each one in the middle. This is the only way that makes sense. And so that is what it is. But with formal charges, putting our negative, oxygen is 6 minus 4. So it ends up with a plus 2. Carbon is 4 minus 6. So it gets the negative 2. And nitrogen would be 5 minus 6. Again, the 5 is the group number. And the 6 is the number of dots and lines. So we get negative 1. Wow. Those numbers are not 0, 0, negative 1. So it's just a bad idea. And it would not happen. It's possible in the lab they could make it. It would probably be explosive, toxic, not a good idea. All right, that's it for formal charges. You'll probably see 1 question in the homework, maybe 1 question on a quiz or your take-home exam, and you'll have your notes, and we'll do another practice. But let's do this situation, which is, what do we do with organic molecules? And organic molecules are carbon-based. And the thing about organic molecules, sorry, I'm going to adjust because we're getting uglier. And I'm not sure if I can do much about that, but I think you see it good enough. All right. So, carbon-based, and why this is interesting and why I want to show you, because it shows up in your lab, and we're going to be doing a whole lab on organic, and we're going to run into them. Because you and I are organic-based, this planet is organic-based at this time. And how do you determine geometry when you have multiple centers? So there's a couple things that happen. First of all, both of these are the same molecule. And this down here is going to be something you're going to probably see me do because it's so much easier than always writing in the carbons when we deal with really big molecules. So this zigzag, we don't show it, but it's a carbon. And if you want, we can write in a little carbon, a little C. And this zigzag here, this would also be a carbon. And we'll see some more in our next example here. And carbon always makes how many bonds? Oh, the cow knows the answer. What'd you say? He says 4. Carbon makes 4 bonds. So if we look at this carbon here, it's got a double and a single on each side. That's 4. This carbon, we only see 2 singles, and so this is part of the shorthand beauty, that there would be a hydrogen above and a hydrogen below, and we don't show it in the zigzag sticks, and that's why it comes out like that. The advantage of the zigzags, it's so much simpler and cleaner. Once you get used to it, and once you know this magic trick, you can see all those pieces in there, and it also shows the geometry a little bit better. But let's go ahead and walk through this. The carbon, this carbon in the middle, the monkey in the middle, it's making 4 single bonds. 4 single bonds is a tetrahedral. 109 degrees. So you just look at that one carbon. It just takes practice, like anything in life. All right, if we look at this carbon, put a star on this carbon. The starred carbon, it is not a tetrahedral. And that is because this carbon only has 3 things around it. So that double bond took away our tetrahedral possibility. So 1, 2, 3 means it is planar. Don't just say planar, because planar just means flat. So we have planar square, we have linear. This is a planar triangle. And don't just say triangle, because we have the pyramid that's 3-dimensional triangle. So we want both those words there. It's a flat triangle, 120 degrees. All right, let's keep going with this. So this carbon here is the same as that. We'll put a star. I'm going to erase it. That was our starred carbon. I want to also do this oxygen. And so the picture's actually showing it nicely. That oxygen is bent. It's a tetrahedral bent. I moved classrooms on you guys again. I'm back in our original classroom. I thought, you know, I've taught in here for decades, really. And so I see all my old students. The problem is, if you remember, it's really warm up here. And it's really warm. Actually went to the other classroom and there were people in the next room and they were really noisy. So we'll be in here today. This is a structural formula, not a Lewis structure. And we're going to see these in the next set of videos for week 2. They don't show the dots. Oxygen obeys the octet rule. So carbon, nitrogen, oxygen, fluorine. That is who the octet rule is for. And so it has 2 bonds, and that would mean we're not showing the dots. Let's do them down here. And so you need to know those dots are there. So the Mickey Mouse ears, Mickey Mouse is on his head, or they could be the eyeballs of our squid, which would be 109-ish degrees. Nitrogen, let's talk about nitrogen. Same thing, nitrogen obeys the octet rule. So it has 3 bonds, and what they're not showing you is the lone pair. And that lone pair on the nitrogen ends up giving it really special qualities. Nitrogen acts as a weak base because of that lone pair. It attracts hydrogen ions, and so that ability to attract hydrogens makes it basic. This is an amino acid. This actually is glycine, and you guys remember you're going to be doing a molecule paper or a compound paper, so you could pick something in the ionic realm. Glycine is an amino acid, and a lot of people who are into bodybuilding believe in taking amino acids. Glycine is also something like 50% of your muscles is this one amino acid, and so after a workout, glycine, actually your muscles break down because glycine goes into your body to help rebuild it. Actually, sorry, that's not glycine, that's glutamine, another amino acid. So any of those would be really cool topics. I have a couple more in the next board. And on next week, I have some more ideas because some people have been emailing me and saying, I need inspiration. So I'm trying to give it to you. All right, the nitrogen, 1, 2, 3, and there's a 4th piece. So 3 bonds, 1 lone pair. That is a tetrahedral pyramid. 109 degrees. And you're going, oh, Dr. Sherpa, you can't just say pyramid. Now, if you say tetrahedral pyramid, I know you mean triangle-based pyramid, and I would show you some grace. But you are correct. You should tell me it is a triangle-based pyramid. But again, if you say tetrapyramid, you are telling me it's a triangle-based pyramid. Nitrogen actually loves that configuration. We're going to do one more thing with this one while we're at it. And so that's how we would look at, you have to look at each carbon and look at how many things are around it, or the nitrogen when you have multiple centers. And we're going to do another practice with that. And this was actually the exact same molecule, just a different way of showing it, where we don't write in the carbons and you don't show hydrogens that are attached to carbons. But do notice you always show hydrogens if they're attached to the nitrogen or oxygen. The last piece I want to do, you all know what it is. It is why Mama Polar Bear is here with her cubs. And is this polar or non-polar? Well, we have that greedy corner, and it's called Noth. And I forgot to tell you about this in the other video. But Noth, if you put a little G here, Noth is actually the hat that gnomes wear. It's called a Noth. But you didn't know that. Now you do. And that is going to be something we build on for these first 5 weeks when we're virtual. All right, if you see Noth, nitrogen, oxygen, or fluorine, they're going to pull. And so this thing is polar. And Liz, everything was the same, which it's not. We can see the zigzags, and it is the oxygen that's pulling, especially OHs, really polar. And we're going to get into that more. So the pull is pulling towards the OH. This is definitely polar. Mama Polar Bear is going to give us a high five, and we're going to move the cow and the polar bear to help us with isomers. Okay, and we're going to move you guys. We're making a whole nother video. The idea of really short 6-minute videos, well, you guys can give me feedback, but in the end, it's going to be my decision. So there's an idea out there that all our videos should be no more than 6 minutes. And then there's another idea, let's just give you the whole lecture like we normally do, and you can pause me and go and do stuff and then come back. All right. So you can pause me if you want, or we can keep going. So the next piece on this page, page 6 still, is isomers. So I wanted to show you an example. And I also wanted to show you with zigzags so you weren't scared of them, because they're out there. These are all carbons. If you want, you can absolutely write carbons in really tiny there. And remember, carbons always make how many bonds? The cow is doing a special meditation. The cow says 4 bonds. So we're not showing them, but there would be a hydrogen above and below each one of these. What the zigzags are showing you is the shape that these carbons in the middle are all tetrahedrals. 109 degrees. We do have one more carbon, and that is here. And that carbon is not tetrahedral. That carbon is planar triangle. Oh, and look, we have it again. We have an amino acid. This is an amino group. You don't need to remember this. We're going to talk about with organic chemistry. But a nitrogen is called amine, and this is an acid, the double oxygen on the carbon. And so amino acids are in our body. This was the bonus question that was in that first email that about half of you got. This is GABA. Actually, I take that back. That was my other class. I think only like 4 of you answered my email, and only 2 of you got it fully right, that there were isomers of it. And those of you who did answer, all 4 of you, I replied with either thank you for looking up the word and seeing that there are actually 4 ways to do this. But this is GABA, and it stands for gamma. You don't need to know all this, but it's really cool. The G is gamma, and then the ABA is aminobutyric acid. We're going to be doing organic chemistry next week, and remember, you're always going to have your notes, but there are some of you who are really into this stuff, which is awesome. Bute means 4 carbons, so 1, 2, 3, 4. We always start with the oxygens get to be at the end closest to number 1, so that's what the butyric means. Acid is because this is an acid group. This hydrogen would actually not be in there in your body. Amino because there's a nitrogen group, and it's called gamma because of how we count in amino acids. This is called the alpha position, this is the beta, and this is gamma. So the nitrogen's on the gamma position. I mentioned this and I used this in your first email because GABA is in our brains. It's amazing. And you make more of it when you calm down. Like our cow and our polar bear, they're just loaded with GABA. GABA is very calming. It has a counterpart called glutamate, and glutamate is more stimulating, and the two of them balance, and we need that balance, and it helps to even out all that chatter in our brain. So there's a whole slew of neurotransmitters. They're always finding new ones. So that would be a cool topic for some of you if you're into brain chemistry. But GABA is really awesome, helps you to meditate. It's going to be an extra credit is, again, for you to meditate. Sending love. This time, instead of being about yourself and cations, it's going to be about sending love out into the world because we need that. And calming and peace and joy. Joy is really where it's at. My mom needed me well. All right, this one is an isomer. And I am going to erase some of my work here. But it has, so we can see the picture, it has the same number of carbons. So carbon, 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 carbon. So it had 4 carbons. They both had 4 carbons. They both have an NH2 group. They both have the COO group. And then if we look at the other hydrogens, we have a hydrogen, 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 hydrogen. And here on the carbons, this carbon would have another hydrogen. I'm just going to show it as a stick. This carbon would have one above and one below. And this one would have hydrogens all around it. So those little sticks are just representing hydrogens for right now. So they both have the same number of hydrogens. So they're an isomer. What we did that's different, let's erase all these sticks for a moment. Those sticks help you to see that they were tetrahedral. All right. We took this NH2, which was on carbon number 4, and we moved it to carbon number 2. So we moved it over. And that's the alpha position. And so that is called alpha aminobutyric acid, so AABA. And there's actually another possibility to move it down number 3, which is beta aminobutyric acid. And so 2 of you, which was actually Davis and the original Aaron. So Aaron, if I haven't told you this yet, there's another Aaron in the class, or there isn't right now. We'll see if they decide I'm too much with this hat on for them. All right, so that's the idea of isomers. Isomers are common in biochemistry and organic chemistry. So when you have, they exist 2 times that you could run into them, and we're going to do some practice in a moment. The 2 times, and I mentioned this in your lab, is if you have multiple carbons and different things on the carbon, so you can rearrange how the things are. So like we have nitrogens and oxygens, so we can move them around. The carbons didn't really do much. It's the nitrogen that moved around. And the other time you can have an isomer is when you have an expanded octet, when you break the octet rule, when you're not enough for carbon and you obey the octet rule. And so let's turn the page and see what happens. So go ahead and stay over here so I don't have to move the computer. And this says it's our practice quiz, but for the first half of the term, you are not going to have quizzes. You will have homework. You will have worksheets. The worksheets are actually already stronger than the quizzes. And so the study sets, I am going to post an answer key for you, so you can absolutely always check your study set. You will submit it to show me you did it, but I am not going to be checking your study set other than to see that you made an effort. I'm not looking to see if you got it right. I just want to see that you made an attempt at it. However, if there's, let's say, 20 questions and you only tried 10 of them, well, you're only getting half credit. Your study sets this term are 10 points. I upped it because they're a lot of work, right? And because I got rid of quizzes. Partly because the amount of things you guys are going to be submitting by email was going to overwhelm both you and I. So you're going to have study sets, you're going to have worksheets. They're both worth 10 points. The worksheets are shorter, but they are a little bit more challenging. They'll make you think. Those I don't post an answer key for. You'll submit those. I will grade them. and give them back to you, or post the answer keys so you knew how they went. And then you'll have a take-home midterm for your first midterm, and then we'll see where we are in a month from now. All right, so practice quiz are still good practice. And if you have the notes, you could already go ahead and try the page, and if you don't, let's just do it together anyway. So here's our molecule, and we're going to go this one from left to right, just because that's how we read. I'm going to call this carbon number 1, carbon number 2, and carbon number 3. And the question I asked, what is the geometry at each of these carbons? And then what is the bond angle? So carbon number 1, 1, 2, 3, 4. So this is a tetrahedral, 109 degrees. My middle carbon is planar triangle because it has 1, 2, 3 things around it. So the double bond only counts once. It does have 4 bonds. So this would be the planar triangle, 120. If you do the lab, you're going to know all these, but again, you'll always have that chart to look at. You just have to be able to draw your pictures right. Number 3, we're back to a tetrahedral. So I showed this picture this way. Sometimes you will see the hydrogens shown out, and this is a condensed form. This means there are 3 hydrogens on the carbon plus that other bond. So there are 4 separate things around the carbon. 4 means a tetrahedral, 109 degrees. So that's our geometries, that is our bond angle. And then I ask, is the molecule polar? And the answer is, from Mrs. Polar Bear, she's like, absolutely. And it is because of the oxygen. So it is polar, oxygen pools. Because it is greedy. I'm not going to ask you why, but to make sure you've all got that, that's one of the big things. If I asked you to show the polarity, you would show the arrow towards the carbon. And actually, if this was drawn showing the bond angles, you would show the carbon like that. If we want to show it with zigzags, it'd be shown like that. That's all it would look like. These ends are carbons. We don't show the hydrogens. We do show the double bonded oxygen. And so that's how that would be shown in a condensed structure. All right, now what we're going to do is we're going to do Lewis structures. For SO2, I'm going to erase so I can just stay in this area. And I lost my eraser. All right, so go ahead and try your Lewis structures. SO2, C2, H4, Cl2, and Se, Cl2, F4. And put me on pause. Go ahead and try it. Actually, don't put me on pause yet unless you have the sheets. You're going to do your Lewis structure, and then you're going to describe it. So you're going to do your Vesper, your bond angle. Is it polar, non-polar? And then we're going to do isomers way down here. I'll move the computer a little bit while you put me on pause. The Vesper and the molecular geometry. All right. Count your electrons. 18. 8 plus 4 plus 14. So 26. This will be 6 plus 14 plus 28. 48. All right. And again, this is why I have virtual office hours. It's going to be mandatory. I already talked to you about this. Once a week, you do have to check in. You're welcome to come in twice a week. So I have office hours twice a week, our normal class time, but not the whole time. All right, so let's do our first one, SO2. So sulfur is in the middle, octet rule. And before you go double bond crazy, sulfur, there are still more electrons. Use up your electrons. Now we have 18. 8 plus 8, 16. So we're going to erase 2 It doesn't matter which two you erase, because this is special. And it did say isomer or resonance. And this one, this very first one, is a resonance. You, again, to know you have a resonance, double and single to the same element. I did this one because I also wanted to do formal charges with it, but let's finish the chart for SO2. So SO2 has 3 clouds, so we would say it's a planar triangle, but one of the clouds is a lone pair. So if you have a lone pair on the center, you're going to have a second answer, which is the molecular geometry, and so you would say bent. And I apologize, there seems to be a lot of glare. 120 degrees. It is polar because of the bend. So if you want, you can redraw it, right, where you show the oxygen and the double bond, and so you can see the bend. In fact, if I asked you to show the polarity, you would have to redraw it, showing the bend. So you could show me the polarity is towards the oxygen, so the net polarity would be pulling, the 2 oxygens are pulling down. It's not linear, they're not straight across. So you would only have to redraw it and show the polarity if it's a question that specifically asks that. I did want to do a formal charge with this. So you can go back to, there's space at the bottom page, or you can go back to your notes on formal charges. And if you look at SO2, and you do formal charges, oxygen, sulfur, and oxygen are all in group 6A, so they're 6 valence electrons. And then this oxygen would be 6 minus 7, the sulfur would be 6 minus 5, and this oxygen would be 6 minus 6. So what I'm subtracting is the number of dots plus the number of lines. So we get a -1, a +1, and a 0. Overall, it comes out as 0. The answer is not 100% correct, and that's what I wanted to show you. And this happens with resonance. Those oxygens, again, are equal in a resonance structure. The gnomes know. The polar bears know. The cows know. And you should know too. And probably rainbow squids, they're so far beyond us. And so what that means is this is really a 1.5 bond. And so we still keep the +1 here, but these two are going to split equally. And so when you have a resonance, the 2 sides or 3 sides will split and all end up with an equal. So they're both a -1/2. Really, this is not that big a deal. It's not going to make or break you, but if you have a question, that's why I have virtual office hours. All right. Let's do our next one. So the C2H4Cl2. And we have 2 carbons. That means you're going to make the 2 carbons in the middle. Carbons want to be in the middle. Don't try to put halogens in the middle. On the periodic table turns out to be arranged similar to how they would be. All right, so we can put 2 hydrogens on each carbon. So we have a total of 4 hydrogens, and then 1 chlorine on each carbon. Carbon makes 4 bonds. It's a shortcut for figuring this out. The dots would only go on the chlorine. Don't want to go to hydrogen hell. And you can count 8 plus 8 gives us 26. You can keep counting as much as you want. These carbons, they're tetrahedral, 109. And this is polar. We are pulling down towards the chlorines. The reason I have this question, I wanted to do this practice, is this is an isomer. We can make an isomer. Keep the carbons in the middle. So an isomer doesn't mean make anything you want, even though that's not possible at all. Like what we did with formal charges. We never use formal charges. So this is not an isomer. What a lot of students will do is, so I'm just going to put lines right now. For those are the hydrogens, but you cannot just say, okay, I'm going to put 1 chlorine up and 1 chlorine down, because these are all single bonds. We're going to talk about a lot of these things in more detail next week. Single bonds are sigma bonds, and they rotate freely. So this chlorine being here, here, or here is actually always the same thing. All right. So what's the other possibility is you actually completely move one of the chlorines to the other carbon. So the isomer would be both chlorines on one carbon, and then the hydrogens would fill in all the other positions. So every carbon is still making its 4 single bonds, and the chlorines would still have the dots. We still have a tetrahedral, although sometimes isomer, the geometry will change, but we actually had to physically pull a chlorine off and attach it to a different carbon. So it's going to be attached in a different place. That is an isomer. Again, multiple carbons, isomers happen, and in my last example it will. Because what happens here is we're going to have an expanded octet. So one center. Really common question students will ask me, how do I know when I can do multiple centers like up there? I rewrote your notes after I came in here and videotaped because I realized the amount of contact time I'm going to have with you isn't going to be as ideal as it may have been. Carbons, when you have multiple carbons, you will have multiple centers. Otherwise, you're going to try and keep everything with one center. Selenium can go expand beyond the octet because it's in the 3rd period. Once we get in the 3rd period, d orbitals are available. On the periodic table, we don't show the d orbitals yet, but they are available. All right, so you would show your dots. And we have 6 atoms around the center, and they each have 8 electrons. 6 times 8 is 48. We're good. This is an octahedral. All the angles are 90 degrees. So an octahedral, again, is we have a square, something above, and something below. You can turn it, any way you turn it, everything's symmetrical. So we can think of my fluorines are in my square, and my chlorine is going up and going down. The other way to think of it is in an octahedral, something is always straight across from something else. My fluorines cancel out, and my chlorines cancel out. This is nonpolar. Now, you might be saying, but Dr. Sherpa, I drew it a different way, because we're going to make an isomer. And the other way you can draw it, let's remove the camera. Maybe we can get rid of some of the glare. Maybe you guys don't see the glare like I see. Right, selenium. Oh, we can put a chlorine across from a fluorine. So basically, what happened now is my square has chlorines and fluorines. Across from this fluorine is a chlorine. They don't cancel out. So there's going to be a pull towards the fluorine. This is polar. And that's the idea of isomers. Multiple centers, expanded octet. And again, your lab is going to give you lots of practice. Everything